Go. Yeah, it's recording. It says
Alright,
record.
looks like we're stuck here. Just a second. In fact, this is lecture 8, not lecture 7. Let me just correct that. Okay. Now we're gonna make a start on palladium cross-coupling reactions today. I don't know if we're gonna get through it all. No problem. I don't know if we're gonna get through it all today because it's a lot of stuff. It's a lot of new things. And we're going to look at an overview of all available CC bond formation reactions mediated by palladium, which is super, super important in the realm of modern organic synthesis. Now, some of you, I think all of you, are familiar with Grignard reagents, right? And they're very versatile reagents in making CC bonds as well, right? I think I've shown the scheme in a couple of my courses, including the 2000 course. This is an overview of what you can use Grignard reagents for in CC bond formation. For example, if you look here at these two lines here, you can in principle make carbon-carbon bonds using Grignard reagent. But the problem is, right, it's kind of cumbersome to make them. And the other problem is that there's always a problem with selectivity. Not always, but very often with selectivity in the CC bond formation. And also, the other problem is that sometimes these CC bond reactions mediated by Grignards are very slow, right? They're very slow, and sometimes they could take up to days to actually react. So we need something new that gets CC bond formation going faster. This slide over here sort of highlights the problems associated with selectivity in CC bond formation using Grignard reagents. So remember, what we typically do is we take a Grignard, which is essentially a nucleophile, and we react it with an electrophilic reactant. So for example, Y here would be a halogen, and then we get a CC bond reaction. And the problem is it doesn't always go that way. You have all sorts of competing reactions taking place. What often happens is you have a radical pathway which leads to sort of the undesired products. You have a possibility of elimination reactions, right? And the other problem is also, so here you can actually see what's actually formally happened here is you've had elimination of HBr, and you've protonated this guy here, right? And you've eliminated magnesium bromide. So you don't end up with a desired product. That's the desired product, the CC cross-coupling product. But you can basically see Grignards, there is a problem with selectivity going on. Now, that's of course a problem. Another problem that you typically have with alkyl Grignards, if you're trying to cross-couple them with alkyl bromides or alkyl halides, is that you get homocoupling. So you get this exchange of the magnesium bromide hopping between the two substituents, right, because you have the Schlenk equilibrium, remember. And then you basically get cross-coupling with the, for example, that guy then would react with that starting material, so you'd get a homocoupled product, and the same thing for this guy here. So there's a problem with selectivity using Grignard. So we need something new in our toolbox to overcome that problem. And we need something that's going to give versatile CC coupling to a broad repertoire of sort of starting materials. So this has in fact been since the since the early 1960s, I would say, early to mid 1960s, been a growing field. And it culminated in a Nobel Prize shared with these three guys here for actually palladium cross-coupling reactions. So the overall principle is that you basically take an alkyl or an aryl halide, or some organic halide. It doesn't have to be a halide, it can also be a triflate. Does anyone seen what is an OTF group? Does anyone know what that is? A triflate is a very good leaving group in organic chemistry. This is a triflate group, used very frequently. That's triflate, abbreviated OTF. So that's a great leaving group in organic chemistry. If halides don't work, it's got a great leaving group potential. So the overall picture is we're taking organic halides or triflates and we're cross-coupling them with some other group, R is some organic residue, with some group attached to that which varies, right, which varies. And depending on the identity of that group, we have different types of cross-coupling, which we're going to look at now. So you get Suzuki coupling, Negishi, Stiller, Hiyama, Kumada, also Sonogashira, etc., etc., etc. There's a whole variety of these. And their difference ultimately is just that we're using a different reagent here for the R2. But ultimately it's catalyzed by palladium or nickel, typically palladium actually, and you form the desired coupled product. So this is now the second Nobel Prize that we've encountered for catalysis. What was the other one? Correct. Haber-Bosch as well, yes. Exactly, good. So you see it's important. Ziegler-Natta. Right, so actually every lecture we've had a Nobel Prize, right? That's right. So, so this is a very powerful tool, and you'll see we're going to look at some examples today of how it's used to make hitherto inaccessible biomolecules and pharmaceuticals in a very elegant way. So this is where we start looking at the art of synthesis, right? Not doing things the classical way, using classical organic transformations, but using these new catalysts to do very difficult things that, with a toolbox available to us in organic chemistry. And that's why they won a Nobel Prize. Now don't get overwhelmed with this. Right? That's the important thing. You will see that all the reaction mechanisms are ultimately the same. Okay? They're ultimately the same, the catalyst cycle, for all of these different cross-coupling reagents. And just to highlight this again, this is what we're talking about. We're talking about this cross-coupling and varying the reaction partner, the nature of the reaction partner to induce this coupling. That's basically what it is. And depending on what what M is, if it's a boral, if it's some sort of a boron-containing group, it would be a Suzuki coupling. If it's a zinc transfer reagent, Negishi. Tin would be a so-called Stiller, Megita-Stiller. Hiyama is with silicon, and so on. Okay? But the connecting theme with all of these coupling reagents is that the catalyst cycle effectively always looks like this, or basically. You start off with a palladium 0 reagent, okay, the catalyst, and the classic one, so we're now talking about palladium. The classic catalyst is PDPPH34. Now that has got how many? That has got how many valence electrons? This guy. 16. 16? No. It's palladium 0. 18. It's an 18 valence electron complex, okay? And, but if you throw this in, so this is the pre-catalyst, a classic example for cross-coupling reagents. Of course, in solution, it can lose a phosphine. There's an equilibrium, coordination, decoordination, and you get PDPPH3. Or even 2, right? You can lose another phosphine in principle and get PDPPH32. So this is 16 valence electrons, and this is 14 valence electrons. And those guys are sort of the active catalyst species in these CC bond reactions, are coordinatively unsaturated, low valent palladium systems. Okay? I should mention that I've actually myself made this compound. It was one of the first reactions I carried out as a PhD student, and I made a huge Schlenk tube full of it. It's a sort of a lemon yellow compound, and I made about 20 grams of those. And my supervisor was very upset with me because he said, you know, palladium is very expensive. But I don't think I'll ever run out of this reagents in Bonn until he retires because of the fact that I made a huge Schlenk tube of it. I also made another one, which is, I've made this one as well. So you can isolate this. It's much more reactive because it's 16 valency electrons, but it's a beautiful crystalline, it looks like glitter, like gold, yellow material. So it's not that difficult to make them, all right? But anyway, these are the active catalysts typically in these CC bond formation reactions. And the first step is always the aryl, alkyl, vinyl, whatever halide. The X is a halide or triflate, remember. Oxidatively adds over the palladium 0 center, right? You get oxidative addition. You then get something called transmetallation. So we've now got a palladium X bond here, and now one of these reagents comes along. Remember, we have a variety of them. And it basically introduces the desired group that we want to couple to this red R onto the palladium center, and the final step is reductive elimination and regeneration of the active catalyst. It's as simple as that. So, and we're going to look at the different mechanisms for the different types of CC coupling reactions in a moment, but it's generally oxidative addition, transmetallation, reductive elimination. Okay? And a very versatile tool indeed. Any questions? Everything clear so far? So let's now get into it. The story starts in the late 60s. So Heck, the first type of coupling we're going to look at is called a Heck type coupling, also called Heck olefination. Okay, it was originally called Heck olefination, named after an American scientist Heck. Now, Heck was working on this in the United States, and so was a Japanese scientist, Mizoroki. So there's a very big tradition of these CC coupling reactions in Japan. You'll see a lot of Japanese scientists. So these two guys were sort of competing to do palladium catalyzed CC bond formation, and what they were basically trying to couple, look at the seminal paper, is taking, this is basically ionobenzene, and couple it to an alkene, all right? That's the alkene, right? They actually start with an alkyne, and then they throw in a base. We're actually going to study this paper for today's PBL session. But basically, it's an alkene aryl halide coupling, and they got it right, and they did this reaction under different reaction conditions and managed to get the coupled product using palladium dichloride. Now they've used palladium dichloride, okay, but they've added a base. There's a base in this reaction. So actually, the palladium dichloride in situ in the reaction reacts with a base and is converted to palladium 0. So very often with these coupling reactions, and this is an important point, they start with palladium 2, like palladium dichloride, palladium acetate, etc. But there's always a base present, which in situ reacts with that palladium 2 reagent to convert it to palladium 0, which is then the active catalyst. Simply because palladium 2 salts are much easier to handle and more accessible than palladium 0. Like I said to you, you can make these guys, but they're quite air sensitive. Much more convenient to start with the palladium 2 reagents and just generate the active catalyst in situ. And that's what he basically did. And actually, the funny thing is, his publication was in February 1971, and Heck published his in 1972, so received January 1972. And if you read the introduction, I find it quite funny, because obviously the reactions are very similar in a way. But he says here, Mizoroki and co-workers have recently reported a palladium-catalyzed arylation reaction of olefinic compounds with aryl iodides and potassium acetate and methanol. We have independently discovered this reaction and find it that it can be carried out under much more convenient laboratory conditions that were used by Mizoroki, and that the reaction provides an extremely convenient method for preparing a variety of olefinic compounds. So you see he's trying to sell his paper because he's doing kind of the same thing as Mizoroki, but he says his reaction conditions are more convenient. In the end, I think it's personally a little bit unfair that it's called Heck coupling. I think Mizoroki should have gotten some of the credits as well. Heck is typically what scientists call this sort of coupling, but as you can just see, one of the seminal papers was from Mizoroki, although both of them were working on it before these seminal reports, and actually since for the whole of the 1960s, so there's a lot of papers that came before these traditional seminal papers of this coupling reaction, but history sort of remembers Heck as being the guy that really pioneered this development. So this is basically what's happening in a Heck-type coupling reaction. We're coupling an aryl halide or a vinyl halide. Now what that basically means, a vinyl halide is something like this, right? In other words, it's essentially just an alkene with some group here. Strictly speaking, this is a vinyl halide, but you can also put an R group on here. You can still do the coupling. So that's what we're coupling, right? We're coupling that with activated alkenes. Now that basically is an alkene that bears some sort of it doesn't have to be activated, but this reaction works better if you have some sort of a substituent attached to the alkene. Like here we have an ester functionality, which sort of activates the CC double bond and promotes the reaction. But you can, in principle, just do it with a normal alkene, right? So we need an alkyl, so we have typically here shown an aryl halide and an alkene. That's Heck coupling, mediated by palladium. Let's look at the steps. We start off with the palladium 0 species. This is, for example, tris triphenylphosphine palladium, right? L is here just representing, for example, ligands. This can be generated in situ from a palladium 2 source, which is typically the case, but you can just throw this in, it will work like a bomb. And the first step, of course, is that we have ligand dissociation, like I've shown here. So we end up with this hot potato here, this 14 valence electron palladium 0 complex, right? And then we have oxidative addition of the aryl halide over the palladium center. So the first step is oxidative addition, right? Then what happens is, in the second step, which you can see here, what is happening in the second step there? Can someone tell me? Sorry? Insertion. We have a sort of a direct insertion. What you could actually break this down into two steps if you wanted to. The first step could be removal of another ligand here, so that goes out. The alkene coordinates, and then inserts into the palladium aryl bond. But I've just shown it here as one concerted step. In other words, because what would then happen is the palladium would, of course, in fact, let's write that down, stepwise. So that we can keep track of the electron counts. Okay, so we've got now PDL, L is a phosphine typically, doesn't have to be. And here is our phenyl ring and X. Now, these are phosphines, so they can come on and come off from the reaction, right? So let's imagine we have this. Now this is going to have how many valence electrons? 14, it's palladium 2. This is palladium plus 2. So this is 8, 9, 10, 11, 12, 13, 14, 15, 16. And this is 14. Both of these species in principle can accommodate an alkene coordination to get the 18 valence electrons. Do you see that? Okay? So it either goes on here, and then the L goes back on again, or it goes on here. So we have now alkene coordination, and following the alkene coordination we have insertion of the alkene into the metal aryl bond, and we end up with this intermediate here. Does everyone follow that step? That's a hot potato, right? That's a hot potato, because what we have then in the last step is, what do we have going on here? Yes, exactly. Beta hydride elimination. That's what we have, isn't it? There's the beta hydride. It gets transferred to the palladium. We get this guy here. And then we left with the palladium-2 compound. You see, this is actually how one generates actually a palladium-0 active catalyst from a palladium-2 species. We end up with this palladium hydrobromide, which is formally oxidation state what? 2. This is palladium-2. It reacts with the base, the phosphines go back on, and we're back there again. So we've done a CC coupling reaction between an aryl halide and an alkene. That's Heck coupling, mediated by palladium-0, which could be generated in situ from a palladium-2 precursor and a base. Let's look at the cycle again as a cycle. Right, this is sort of looking at it in a more detailed way. Let's start here. This is the starting point. Let's follow it step for step. Palladium-0, how many valence electrons? 14. 10, 11, 12, 13, 14. Oxidative addition. How many valence electrons in this guy? 16. Alkene coordination, right? Alkene coordination takes place here. You see, one of the the phosphine is still sitting on here, but that phosphine can in principle also go off and on, because remember these are in equilibrium. It doesn't have to, because if the alkene coordinates to the palladium to form this 5 coordinates pi complex, how many valence electrons does this guy have? Well, it's 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Is 18 a good number? Yes, the 18 valence electron rule. So that's possible as an intermediate. If the phosphine were to dissociate, we'd have how many valence electrons? 60. It would be an even hotter potato, and the reaction would probably go faster. But anyway, this is a reasonable intermediate, and there is experimental evidence for it. And now we have what happening? We have now insertion of the alkene into the metal aryl bond. We end up with this species here, a sigma intermediate, 1971, right? This is work of Heck, it's actually 1972, but okay. Then we have the beta hydride elimination, right? We form this guy here, and then we form another pi complex. Remember, if you have beta hydride elimination, you always form immediately after that a hydride alkene, and then the alkene can dissociate from the palladium, so that's the product. And then we're left with this palladium-2 guy here. That's the product resulting from the beta hydride elimination. And now we have a base, some sort of a base that comes along, a Lowry-Bronsted base or a Lewis base, and it picks up this H. You get a formation, let's say, of HBr, right, mediated by the base, and you're back at this guy here. So in fact, to go from this palladium-2 species back to palladium-0, you need reductive elimination of the HBr, right, to get palladium-0. And that's facilitated by a base. So the base picks up the proton, and then you have formation via reductive elimination of that. So that's Heck coupling in a nutshell. And are there any questions? Heck Mitsuroki coupling. All right, let's go to the next CC coupling reaction. Oh, before I get to coupling, we're going to discuss each of these couplings, and then I want to show you 1 or 2 examples of how they're employed in natural product synthesis or organic synthesis, just to show you the power of this work. So here is an example. This is the synthesis of Taxol, which is an anti-cancer drug. And one of the key steps, you see here they've directly used palladium tetrakis triphenylphosphine. This is the base, the potassium carbonate. What has actually happened here is we have a Heck reaction between this alkene here, and this is also an alkene with a triflate group, which is the leaving group. Remember, you can do Heck coupling between aryl halides or aryl triflates and alkene halides or alkene triflates, essentially, with alkenes. Better is if those alkenes are activated, like we just saw now with if there's an ester somehow floating around, which increases the reactivity. But you can in fact also just do Heck coupling with a normal alkene, but like we have here. And what you see is you have a very interesting Heck coupling reaction where in fact there is a regiospecific formation of this very unstable ring system here. So you don't have ring coupling from that carbon 1 atom from the carbon 2 atom, and that's because that's driven by the ring strain of the two possible products. So you have high selectivity towards this intermediate, which then via other synthetic steps can be actually not that many. You can just essentially attach this residue to this molecule here, and you've got Taxol, right? So a very important step. Now ask yourselves again, using classical organic synthesis, how would you build a ring like that? It would be very difficult because it's a 1, 2, 3, 4, 5, 6, 7. It's a 8-membered ring, right? And do you now see why it attaches in that way? Because if the Heck coupling were to go in a way that this carbon atom binds to that carbon atom there, we would end up with a 9-membered ring, right? And 9 is much less stable than 8. Remember that discussion we had about metallocycles in I think you gave a lecture on it? It's the same sort of arguments here. The ring strain of an 8-membered ring is much, an 8-membered ring is more favorable than a 9-membered ring. So it actually picks out this the C2 atom here and does the coupling that way around, which I think is a very interesting application of Heck-type coupling in the synthesis of a very important product. Okay, so that's Heck coupling. Let's now go to Suzuki coupling. Now remember, all these couplings are ultimately, in principle, the same. We're just varying the reagents that we couple to the aryl halide or the vinyl halide. Right, it's typically coupling to an sp2 center, which we see again here. So what we have in Suzuki coupling is we have, again, an aryl halide, typically an aryl halide, and we couple it to an organoboronic acid. Now, well, we don't couple it really to an aryl boronic acid, but that's the coupling reagent, all right? So let's just have a look at this. In fact, let's look at the mechanism first, stepwise. We start off with, for example, so what I've represented in this first step here is just how you'd make something like this. So this is a typical Suzuki coupling partner. Let's write that down, because it's important. So in the Suzuki reaction, we're coupling aryl halides with boronic acids, not moronic acids, boronic acids, and they're typically of the form BOH-OH. So you need something like this. This is the ideal coupling partner for a Suzuki type coupling, and you'll see how it works in a moment. This first step here, up until here, is just to show you how one synthesizes those things. So there's quite some versatility. You start off with this guy here, which is commercially available, right? BOCH3, it's trimethoxyborane. And if you react that with the Grignard, you can basically, you basically get this guy here, okay? Now, that can readily be basically protonated to form the desired boronic acid, aryl boronic acid. Now, the great thing about this reaction, of course, is you can play around with the substituents in this ring here. You can build stuff in the backbone here, etc. So it's possible to sort of modulate what the nature of this ring is here by modulating the Grignard. That's the cool thing about this. Anyway, that's an important thing. And again, you use palladium 0. Again, you can typically use palladium tristriphenylphosphine. And here we have an example where we're reacting an aryl bromide that just happens to have an ester in the backbone, doesn't have to have one, it's just an example. And the same thing happens as with Heck-type coupling. The first step is oxidative addition. And what happens now in the second step is always, as we know what, transmethylation, all right? Now, Heck was a little bit different. We didn't really have transmethylation, we had alkene coordination and insertion. But the typical manifold for a palladium cross-coupling reaction is oxidative addition and transmetallation. And basically this is acting as a transmetalliting reagent by introducing this aryl group onto that palladium bromide, right? So you end up with this guy here, and then it simply undergoes reductive elimination, regenerates the palladium 0 compound, and we have the coupled product. So that's a great way of making aryl-aryl bonds, right? Bis aryl substances, which are important. Let's look at the mechanism here represented as a cycle. Palladium 0, oxidative addition of the aryl halide. Here, oh yes, this reaction needs to take place in the presence of a base as well, right? A base. You can use potassium carbonate, you can use sodium hydroxide, any sort of a base. You'll see why in a moment. The oxidative addition actually step results in a palladium halide bond or palladium triflate bond, which then reacts with a base to form something like this. And that then reacts with a boronic acid, essentially, which via this pathway here, you start with a aryl BOH2, which also reacts with the base to form this borate intermediate here, and that guy actually acts as the transmethylating reagent. Puts the aryl group on this boron atom onto the palladium center, and then you have reductive elimination. Questions? Okay. So oxidative addition, reaction with the base. The boronic acid also reacts with the base to form a borate. This is called a borate. This is a neutral borane, and the borate then gives up its aryl group to the exchanges with the OH. So you have a sort of a transmetallation going on there. Then you've got palladium aryl reductive elimination. Okay. So that is basically in a nutshell Suzuki coupling. This cycle here just shows the exactly the same thing, just using a different base. So here I'm using sodium tertiary butoxide. It doesn't matter. You can use sodium hydroxide. You can use potassium carbonate. Any base will do. So let's just go through the cycle. Palladium 0, right? This isn't a naked palladium atom. Obviously, it's something like palladium bis triphenylphosphine. You know, that's the standard intermediate or active catalyst species. So we have oxidative addition. We have a reaction with a base, converting that X, which is the halide, to, in this case, an O2 butoxide. There we had it converted to an OH. And then, in the second step, the base, as you can see here, reacts with a boronic acid 5, right, bearing an aryl group. R1 is an aryl group. We form a borate, right, and that 6, that reagent then does transmetallation with this guy here to install the R1 group on the palladium, and then we get reductive elimination. So that's Suzuki coupling. And there's several examples of this. Here is a very simple example. Check this out. Here I've got a typical Suzuki coupling between this boron-containing reagent and this aryl halide, and forms this nice CC-coupled aryl product here, which is in fact a precursor for a blood pressure agent. So this is a very important process. And what you can actually see here is you've got two possibilities to play around with substituents, right? You can play around with functionalizing the aryl halide, or you can functionalize the aryl group that you attach to the boron. So there's a lot of possibilities to modulate and change the substituents on the aryl group. Basically, the possibilities are endless. Okay, and this is also a very nice example. This is, again, a blood pressure agent, which is in fact gone commercial, losartan. And let's have a look at this reaction. It's actually a classic Suzuki coupling in this key step here. What are we coupling? We're coupling this carbon atom here with this carbon atom here. You see that? So here, you see what I've just said. We've built this whole thing here, probably made a Grignard reagent of that and put it onto the boron, and then this you would react palladium triphenylphosphine in the presence of a base would give you this coupled product, and that is in fact an well, it's a blood pressure regulating agent. Yeah, so this is an industrial application of Suzuki coupling. And here are some more applications, just so that we really get our teeth stuck into this. Here what they've basically done, you see here they start with the palladium-2 precursor. That's no problem, because there's a base floating around in the reaction mixture, which remember can convert palladium-2 to palladium-0, which is the active catalyst. This is just more convenient to actually work with. So what we're coupling here is, what are we actually coupling here? Yes, that's the triflate group, exactly. That's right. So that's triflate, remember? I drew down the formula earlier. It's being coupled directly with this guy here. And we get this product. This is an acetyl functionality, incidentally, which is quite an important functional group in bioactive molecules. And over here we have another example. Again, this is an agent that stimulates certain electrical impulses in the central nervous system. Again, a coupling between this halide and this boronic acid, and you can see what I've done here is I've actually done the coupling with the pyridine group, which is also possible. So there's quite a high functional group tolerance. That's what we call it. We call it functional group tolerance. What does that mean? Can someone tell me? As the name suggests. Correct, correct. And that's another desired thing in catalysis, because if you develop a catalyst that only reacts if they're under limited conditions, that's not good, right? So you want catalysts that have a high functional group tolerance. And that certainly is the case to a very large extent with these sorts of CC coupling reactions. This is another application in the natural product synthesis of an insect pheromone. Here they've decided to start with a palladium-0 catalyst, 1 mol%, that's the base, sodium hydroxide. This is taken from a very nice article, review article by Nicolau, 2005. And this is a very, actually quite straightforward application of a Suzuki type coupling reaction. Interesting thing is here they've started with a vinyl bromide. You see, it doesn't have to be an aryl, as long as it's an sp2 hybridized carbon. That's a more general way of looking at it. It doesn't have to be an aryl halide, it can also be a vinyl halide, right? Same with Heck coupling. It doesn't have to be an aryl halide, it can also be a vinyl halide, as you see here. And that is vinyl bromine. So, yeah, very versatile reaction, gives access to very important natural products and medical substances. And I think a very versatile reaction in modern organic synthesis. Let's now come to the next coupling, or maybe, in fact, I think we should stop at that point and save this for next week. Because I don't want to sort of flood you with too much information. That clock is wrong, right? What's the time?
45.
So we've got 15 minutes, right? 15 minutes? All right. Okay, let us stop at this point, not stop completely. We'll finish this lecture next week because it's a lot of information to absorb. We've looked now at 2 couplings, Heck and Suzuki. Next week we're going to look at the others, right? So we're going to have a whole toolbox of coupling reactions. Let's now in the remaining minutes of this lecture apply what we've done up until now. All right, let's do that. So I'm going to write down a molecule, and I'm going to show you sort of how this works, or how this can work, and how useful this is. I'm just going to turn this off. How we can employ what we even already know at this point in time. So let's take a molecule. Let me just get a decent pen. So multi-step organic synthesis using catalysis. And this is going to be sort of a silly illustration of that, but it's going to hopefully give you the idea of how versatile this is. So let's start off with a molecule. All right. And let's say I want to convert that somehow to something like that. So, this is sort of also combining a bit of organic chemistry, right? Have you guys done retrosynthetic analysis? Good, good. So, this is kind of a simple example, right, where I sort of mapped the way for you. But let's suppose we wanted to make a molecule like this, which might be a useful thing to have because it's highly conjugated, you know, you've got a CC double bond and stuff like that. Now, we've actually got tools to make that in 2 steps. Right? Don't we? Let's give it a go. How would we make it? Starting with with phenylbromide.
Add it to another aryl ring with a vinyl group on it and OTS.
Let's suppose. Wait a minute. Let's make this a little bit more interesting. Let's suppose I have to make this, but I have these available starting materials. I have that, and I have this. Yes. So these are the 2 starting materials I have. What am I gonna do? It's difficult. This is fun though, right? This is applying what you know. So, okay, we've got this guy here. How about we introduce a vinyl group here? Can we do that? Yes, we can. We can use Heck coupling. So if we take that guy, well, it doesn't have to be Heck, it can also be Suzuki, actually.
Yeah, I was wondering, is there like a reason why you would use one type of coupling over another, or are they just equivalent?
No, it depends. It depends on what you're trying to do, because what I'm glossing over is some couplings work better than others, right? For example, if you have in Heck coupling, if you have an activated alkene, the reaction works. Activated meaning you've got a CC double bond and let's say an ester in the backbone will work much better than if you just have a normal unactivated alkene. So there are these considerations. So yes, it depends on that, but it also depends on what sort of convenient starting materials you have, right? So you can sort of sometimes pick and choose depending on that. Now here we can basically do a CC coupling reaction between this guy. Of course, we're going to probably have issues with selectivity because we might get the dicoupled product. Anyway, let's say for argument's sake we can do a Heck-type coupling reaction with this and, well, what would it be? It would simply be with ethylene, wouldn't it? Or with ethylene. So we would get, we'll get this guy. Now we need to couple this with this, don't we? And how would we do that?
You need to introduce
Oh, as a matter of fact, well, that's, yes, how could we do that? In a number of ways. Well, what we could do simply is make a Grignard reagent out of it. That will probably work. But if we do it catalytically, we can do what? Well, we can there use a Suzuki coupling, can't we? If we convert this guy, if we make the make the Grignard of this, remember that we can convert to this guy, in principle. And if we now react that with this Suzuki coupling, we should get here. Does everyone agree? Remember, Suzuki coupling is an aryl bromide typically and a boronic acid. And there we've got a boronic acid decorated with an aryl group. And we've constructed this aryl group from a Heck coupling. How cool is that? All right, what happens next? We want to take this guy and we want to convert it to this guy. That's a cool. That's a cute reaction. What do you guys think? How can we do that catalytically? Let's say let's start with this guy and get here. Any ideas? Who said that?
Self-metathesis?
Good. Alkene metathesis. Very good. If we do alkene metathesis on that using which catalyst? Grubs, yeah. But if we're not like really professional guys, which catalyst would you use? Grubs 1, Grubs 2, Beta Grubs generation 2, because it's got a much faster rate. So you see, this is just an example I dreamt up, but using exclusively catalytic transformations, you can do organic synthesis, right? That's the point here. And already we have quite a plethora of reactions. Now, of course, I haven't specified the E and the Z selectivity and stuff like that. This is just to illustrate. Let's do another example. All right. By the way, someone